In this video, we're going to carry out the continuity of CPC and polarity tests for a lighting circuit. I'm going to perform it on the first lighting circuit we carry out in the workshop, which is a one-way lighting circuit. I'm also going to introduce the R1R2 link, which I've reviewed on the channel before, to see if it can make this test easier in that college setting. And maybe if you're not in a college setting, you can leave some comments below whether you believe it would work well in industry. We'll also signpost the pages in the on-site guide that can also be used to help you carry out this test. So some of the things I've performed off camera is I've isolated the consumer unit's main switch and I've proved it's dead in here. I've shown that many times on the channel before, and I will leave a link to that video as well. The lock is in place, the sign is here, and I've got the key inside of my pocket out of the way, and I'm ready to perform this dead test. If I look in the on-site guide, I'm looking in section 10 of the on-site guide for testing. And as I turn over the page, hopefully you're familiar with these first tests here, ones that are carried out dead. And the first test says continuity of protective conductors, including main and supplementary bonding. I said I would also include test number 4, the polarity test. And it says here by continuity method. So you can include this in stage 1 testing, and we will. If we look across at the page here, you've got a pictorial clue on how to carry out the test, so we can read the description above, and we can see there is a temporary link from the top of the circuit being tested to the earth bar where the CPC is connected, and that's what we're going to use with our R1R2 link. We're going to make that temporary link shown in this one here, and we'll include that polarity test at the same time. So I've got my Megger 1711 multifunction tester, one I've used many times on the channel before. I've put my leads into the top of the instrument, and I'm using the red and green section. And as always, we've used the red and green lead, but remember, we don't have to. They could be different colors, but as always, we like to keep them the same. We turn it back over. We're going to need to set it to ohms in order to measure the resistance of the cable, because the continuity test is measuring the resistance of the conductors. So we're going to flick that round to the omega symbol. Our instrument comes on. And now we've got to remember the fact that our leads are obviously got copper cables within them, copper conductors. So we need to remove the resistance of those, as well as our link. Our R1R2 link will also need its resistance removing. So I'm going to link them together. So crocodile clip on one and crocodile clip on the other. You see straight away, without even touching the machine, that we've now got a reading on it. It is saying 0, so that's a little bit of luck to start with. If it was flashing 0, we know it's below 0. So it's saying that we've removed the resistance of those leads. But let's show you how we would remove those resistance. We press the test button. We've pressed it once. You can see we have a reading. I press it again. And I'm looking for a stationary 000. So that is not flashing. Therefore, I've removed the resistance of both the link and the leads, so I can perform this continuity test where I'm measuring the resistance of conductors. So the circuit under test is this one here, this B6 amp circuit breaker, so 6 amps type B circuit breaker, and I'm going to need to link together the line and CPC, and on the on-site guide it shows a link between the two. It doesn't show you disconnecting any other elements of the circuit, so we're going to link from here to here. Normally I would have undone this and put either a crocodile clip onto the conductor over to here, or I would have taken this conductor out and screwed it into the earth bar to link these two together. But with this R1R2 link, it removes the need to do that. So from a college point of view, it means we aren't undoing screws more often than we need to, especially when testing. So I'm going to drop this one in, which has got a magnetic tip on it. So I drop that into there to link onto my line conductor, and that's held in place. So I can't pull that away, that's held. And I'll just put my clip across to here to link together my line conductor to my CPC, and we're going to measure the resistance of those two. And when we open and close the switch, we will be able to prove our polarity, that our switch is operating in that line conductor. We've only got one lighting point on the circuit, so we're only going to need to test it to here. In the real world, if there is 10 lighting points on a circuit, so maybe 4 bedrooms, a landing area, an upstairs bathroom, etc., you'd need to do this test at every single lighting point and switch. But in a college setting this time round, we've only got one lighting point and one switch, so we need to prove the CPC gets to here and the CPC gets to the switching circuit. But if there was more than one, you'd have to continue on the test for all of the points on the circuit and record the highest reading. So if we undo here, and we open it up, we can see we've got our connections here. Hopefully we're familiar with the 3-plate method from many videos that I've done and time training in college. So we've got our circuit protective conductor here, and we're going to be going on to our switching line conductor so we can prove that the switch will operate in the line conductor. It's not a neutral, it's got brown sleeving on, it is a switching line, and we've covered that many times on the channel. So I'm going to measure between here and here. I'm going to look at the reading, I'm going to operate the switch to hopefully see full scale deflection, and when I see that full scale deflection I know that switch is operating. So in we come with our connections. So we're going to connect onto the protective conductor. We're going to connect onto the switching line. Now you may have heard a little click noise. So if we go back to our instrument, we can see we've got a reading, and it's going to jump around a little bit. Let's see what we get. 0.09. We have a reading, therefore we have continuity. It is jumping around a little bit. So what, in other words, if we just pull back slightly, we've got a cable from here. So the CPC from here comes to here, and by connecting gets all the way back. So we have a completed circuit. So it will come CPC in, down to the switch, from the switch back and round as a complete loop, and we've measured that resistance as 0.09. We would record the highest value of reading, so we need to remember that one, but I said we were going to perform the polarity check at the same time. So we come to the switch, I'll operate the switch, I've operated it, and we can see now it's an infinite reading. It's gone off the scale. We have lack of continuity, so we've broken a conductor. Naturally, we break the line conductor here at the switch. So we open the circuit. So if we do the switch again, so if I go to that position, I've got a closed circuit. I've got a reading now of 0.1 of an ohm. So it's there, it's jumping around a little bit. So we're back to our original reading. So we've opened and closed that switch. So let's do that once more. So we've opened and closed that switch, and we look at the instrument deflecting, and we can prove that that switch is operational as part of our polarity check, and our readings settle down. We need to leave it in the on position for tests that are carried out in the future. We're not going to carry out them in this video, but the insulation resistance test requires all circuits to be left on, but we're going to leave it on, and we're next going to check the CPC makes its way down to the switch. We also need to prove the CPC gets down to here. We can see it's a fully insulated box and switch, so therefore it hasn't got any metallic parts that would make it an exposed conductive part. So this CPC is down here waiting in case maybe the switch is changed for a metallic one, and then that would be required to be connected to the CPC. But we need to prove it gets down here, because there's nothing suggesting that the minute we've left our installation that these switches are changed. So we need to prove the CPC gets to here. So if we clip onto the connection there in the back of the box, and we come into, and I'm going to go into the top where the common is. It wouldn't matter because I've left it on which one I go in, but I'm into the top position, I'm onto the CPC, and I go back and look at my reading. I've got a lesser reading here of 0.06. I do not need to operate the switch. There's no operating the switch here. We operated the switch to prove it turned the light on and off. We don't need to prove the switch comes on and off. We've already done that. And the CPC is connected to here, and we've got a complete path between the line and CPC back to our linked position within the consumer unit. So we've proved its continuity. We've operated the switch, so we've proved polarity. We need to record the highest reading of 0.09 in our box heading R1 plus R2. We've operated the switch and see the circuit open and close, therefore we can tick the polarity box, and for us that's it completed for our continuity of CPC and polarity test for our one-way lighting circuit. So I'm sure someone's already thought, Gaz, that switch is further away from the consumer unit than that lighting point. However, the highest reading was here, and we know resistance is based around length, so longer conductors have a higher resistance than shorter conductors of the same cross-sectional area. So this is a 1mm squared cable that went to my light and to my switch. So why was the reading higher at the lighting point than it was at the switch? Well, let's think about the circuit that we've just measured its resistance for. The line connection here comes from the breaker. It comes into the loop-in terminal in here, and we've looked at that before in the channel. It comes into loop, it goes down to the switch, and then comes back on the blue conductor identified with brown sleeving, which is my switching line, back to here where we measured its resistance when we're at the lighting point. So we measured from the switching line to CPC here with that full length of run in and achieved our reading. So it came line conductor through, down and back for measured point to here. When we were measuring the CPC and line connection in the switch down here, we had the line conductor from here. So the line conductor came from the consumer unit. It came into the loop terminal and down to that position there. And we measured between the common and our CPC connection. So when we did the lighting point, we actually had an additional piece of cable being our switching line conductor back, which meant the resistance was higher at the lighting point because more cable was in circuit than it was at the switch. However, in your own mind, you're thinking that this switch is further away from the consumer unit than the lighting point, which is true, but the amount of cable in circuit is longer when we measured it at the lighting point. However, I said to you at the start, whichever reading you get, which is the highest, is the one you recorded. Okay, we've used logic here to get our highest reading here. When you're in a full installation, you're going round, it's that highest reading achieved, wherever it is that we would record. So hopefully that's give you a guide on how to carry out that first test that you're probably going to carry out in any electrical workshop up and down the country on the first circuit that you install, which usually is a one-way lighting circuit. I've used my R1R2 link, and I think I've confirmed from my point of view that this is a must for college settings. It meant that I didn't have to unscrew any additional terminals within my consumer unit that obviously can become damaged, and it's quite expensive for colleges to start replacing items within consumer units. Hopefully you've also seen the fact that even though we thought the highest reading may have come at the switch because it looks further away from the consumer unit, that we can see the length of the conductors at the lighting point testing between the switching line and CPC as more copper cable in circuit and therefore a higher resistance. We know that R1 stands for the resistance of the line conductor, R2 stands for the resistance of the circuit protective conductor. So when we inserted the reading of 0.09 into our paperwork, we saw the box heading R1 plus R2, the resistance of the line added to the resistance of the CPC, which we achieved by linking them together within the consumer unit with the R1 plus R2 link. We operated the switch to see the lighting point come on and off. We'd linked between the line conductor and the protective conductor in the consumer unit, and Polarity proves that we switch and fuse within that line conductor, and we prove that so we can give that box a tick. But as always, I just hope this video has been some help.